Today we're going to start talking about series, which is the next thing. But actually, there was one last thing that I wanted to say about sequences first. We talked last time about sequences can be increasing or decreasing, and I will just refresh your memory. Increasing means the definition of increasing. I mean, on an informal level, it just means that each term gets bigger as you go down the sequence. But formally speaking, the definition is an plus 1 is greater than an, or you could write it the other way around, an is less than an plus 1. All right, that means that's the definition of what it means for a sequence to be increasing. And then decreasing is the other way around. Decreasing means an plus 1 is less than an. That is, the next one is always smaller than the previous one. All right, and we also had this word, which I'm going to use some more today, monotone. Monotone, it means that the sequence is either increasing or decreasing. And you'll see some stuff today where we're going to use this word. It's just kind of a pain to say increasing or decreasing over and over again, because there are a lot of things that you can say about sequences which are increasing, and whatever you can say about a sequence which is increasing, you can basically say the same but opposite thing about a decreasing sequence. And so all the things that we talk about for increasing, they kind of go together with the same things for decreasing, and so there's one word to encompass both of those things, and that is monotone. Sometimes people say monotonic, but anyway, monotone just means the sequence is either increasing or decreasing. All right, that's all. We talked about that last time. We're going to mention that this time, but this is not like our main topic for discussion. One other property of a sequence, a sequence could be increasing or it could be decreasing or it could be neither. Another property of a sequence is boundedness. Boundedness, I will say, of a sequence. That is, a sequence can be bounded or not. This is an important property that a sequence can have. And bounded means that basically it doesn't get big beyond a certain point. So there's actually two similar definitions that we're going to have. So we say a sequence an is bounded above. There's some sequences are bounded above. A sequence can also be bounded below. Bounded above basically means there's just like some amount so that the sequence never goes above that amount. And the picture you should have in mind is something like this. There's some kind of like upper limit here, which in this definition we're going to call m. Y equals m, and bounded above just means that the terms of the sequence, they always stay down under that sort of maximum threshold. All right, and that m in this context is called the upper bound of the sequence. But anyway, could I write this in formal language here? It's a little strange to write this down. What I want to say is basically all these numbers, they always stay underneath this m. So bounded above means, first of all, there is some number m, and all the terms are below m. So it says this: a sequence is bounded above when, this is the definition of what bounded above means, there exists some real number m such that all the terms are below the m, and they are allowed to equal the m. So I'm going to say, well, actually in our book they write it this way. There exists some real number m such that an, the terms of the sequence, is less than m for all n. All right? They are down there. If that is true, then we say the sequence is bounded above. That is, there's some big number that's bigger than all of the terms. All right, and in this context, m, the number m, is called an upper bound for an. All right. I said it is an upper bound. I didn't say the upper bound because I think you can tell in the picture. Actually, if there is such a number m, then there's not only one of them. Like you could always consider a number even a little bit bigger. That would also be an upper bound for the sequence because like on this picture, m plus 1 would be like 1 higher than m. But that number is also bigger than all the terms in the sequence. So there's no such thing as just a single upper bound. There are many upper bounds, if there are any. Sometimes there are none. All right, so this is what it means to be bounded above. All right, there's also bounded below, which I think everybody can tell. Actually, the sequence that I put here also, it seems to me, looks like it's bounded below. That means you can put a number down here such that everything is above that number. So I'm going to write that also. This is no surprise. We say a sequence AN is bounded below when there exists. So here there is some number kind of on the bottom. And in our book they use little m for a lower bound. So when there exists a real number little m, such that AN is greater than little m for all n. All right, same picture, but this time the bound is, below everything. And in this context, the little m is called a lower bound for the sequence. All right, the picture that you should have in mind this time is something like if all of my sequence points are up here and there's some kind of y value that's below everything. All right, that's the picture that you should have in mind when you're talking about a sequence which is bounded below. It has a lower bound. All right, and when I just say the word bounded overall, so we sometimes talk about bounded above, sometimes we talk about bounded below. If I just say a sequence is bounded, that means both. So if it's bounded above and also bounded below, then we just call it bounded. So we say AN is bounded, just without saying above or below. We say AN is bounded when it is bounded above and below. All right, and that means there's sort of like one big number and one small number so that the sequence is always in between those two numbers. That's called bounded. All right. You will see some homework problems, I suppose, next time about boundedness. I show you a sequence. You tell me, is it bounded or not? And to be more specific, is it bounded above? Is it bounded below? So here's one like that, and then I have some that you can think about. How about AN equals n over n squared plus 1. Is it bounded above? Is it bounded below? All right. It may be a good idea just to get a feel for this. So my question is it bounded above / below? That's the question. Is it bounded above? Is it bounded below? To get a feel for this, it might be a good idea to just like write out a few terms of the sequence and see if you can see any kind of pattern. Like here, if I were to start writing them out, I would start, of course, at n equals 1. It looks like 1 over 1 squared plus 1, and then 2 over 2 squared plus 2, 3 over 3 squared plus 3, etc. If I were to simplify, just because I want to get some kind of feel for what these look like. The first one, I guess, says 1 over 2. The next one would be 2 over 4 plus 2, 2 over 6. The next one would be 3 over 3 squared plus 3 in the bottom. That's 9 plus 3 is 12. It's 3 over 12. That's a half, of course. That's 1/3. That's 1/4. Did I do those right? I didn't expect there to be such a nice pattern here, but yeah?
Where did the 2 come from?
Oh yeah, that's why. It shouldn't be on the bottom. It's always n squared plus 1. Not. I was doing n squared plus n, which actually simplifies to 1 over n. I didn't want that. Yeah, thanks for that. I knew something wasn't right. That was my April Fool right there. You all fell for it except for her. Great job, Ainsley. So that's a 5 on the bottom, and this is a 10 on the bottom. Okay, so you can't really simplify more than that. All right. Anyway, do these appear to be bounded above? Do they appear to be bounded below? I think actually, just looking at these, it's fairly obvious to me that these are bounded below. Anybody agree? Can anyone tell me a number which is less than everything in this sequence? Any ideas? I think I heard somebody whisper. 0, yes. I thought that she whispered 0. Yeah, you can tell just by looking. I mean, you don't have to look very closely at all to tell. These are always positive numbers, right? And in fact, what I start by looking at, because n is always positive, 1, 2, 3, that's what n can be, then this is always going to be positive, right? There's no way that could ever be negative. So this, even without like looking at these numbers one by one, I think it's fairly easy to see that an is always positive. So that means an is always greater than 0, so it is bounded below. Right? And what about bounded above? That's the other question. Is it bounded above? Now for this one you have to look a little bit more carefully, but you could look at these numbers, for instance. Anybody think you can tell a number that's always going to be bigger than these? Yeah? 1, I think, is a good answer. Like, to me, these all look like, it looks like it's always going to be a fraction, right? In fact, you know, looking at these numbers should be kind of like a vague inspiration, but really your goal would be to look at the original formula and explain to me why this, for instance, is always less than 1. Can anyone have an idea? Just looking at this, can you tell that that really is always going to be less than 1? It is a fraction. Yeah?
It's because the highest power in the denominator, like the power in the denominator is higher than the power in the numerator.
Yeah, I think actually, I think it's, yes, this is why. It's a fraction where the bottom is bigger than the top, right? On top I have just n, on the bottom I have n squared plus 1, and n squared, of course, like n squared is bigger than n, right? For because I'm talking about a sequence, that means n is, you know, 1, 2, 3, 4, etc. N squared is always bigger than n, and so therefore n squared plus 1 is always bigger than n. This is a fraction in which the denominator is bigger than the numerator. That means it's always less than 1. So that's what I'm going to say for the other part. An is a fraction, and the denominator is bigger than the numerator. So that means an is always going to be less than 1. And therefore, it is bounded above, right? So the upper bound for this particular sequence, the upper bound is 1, and the lower bound is 0. All right, so an is bounded above. There you go. All right. So it is bounded below and bounded above. So we can conclude an is bounded. Right? Remember, when I just say bounded, that means both above and below. So an is bounded. Great. I have a couple other for you to think about. I tell you a sequence, you tell me, is it bounded above? Is it bounded below? Is it bounded? Once you answer the first two, you can automatically answer the other two. All right, chat with your friends. See how you like these. An equals 3 to the power n. I also got an equals minus 1 to the n. I also got n e to the negative n. And see what you think of these guys. feel free to chat with your friends. You may want to, write down a few of the numbers to start with to get a feel for it, or not. I'll leave it to you. You could chat with someone you've never chatted with before as a little cute April Fool. Wouldn't that be funny? talk about these. I see some people doing some good things here. For 3 to the n, this one is bounded below because these numbers are always positive, but it is not bounded above. That's because 3 to the n, just like these values will increase forever, right? If you were to write down a few of them, they would be 3, and then 3 squared, which is 9. And then 3 to the 3, which is 27. And then 3 to the 4, which is 81, etc. This I can tell, those numbers will continue to increase forever. So there is no like upper limit to those numbers because they increase forever. So this is not bounded above. Not bounded above because the values increase forever, but it is bounded below. For example, by 0, right? All of these are greater than 0 because you can tell 3 to the n is always positive no matter what n is. So these are bounded below by 0. In fact, they're all bigger than 2 even, but you don't have to say that. You just have to give me some number that they are all bigger than. All right, the next one, negative 1 to the n. This, if I were to write out the terms, looks like this, etc. All right. Is this bounded above? Can you think of a number that's bigger than all of those? What do you say? You can show me on the fingers. What is a number bigger than all of those? I would say this many, right? They're all less than 2. Some people, as I was walking around, they said, these are all less than 1. They're not all less than 1 because some of them equal 1. So you can't say they're all less than 1. They are all less than 2, though, certainly. So these are, I would say this is bounded above by 2. What about bounded below? Is there a number that's less than all of them? I think yes. Negative 2 is below all of them. So it also is bounded below by negative 2. All right, so that sequence on the whole, it is bounded, right? Bounded above, bounded, remember, means that it's both bounded above. So it is bounded. All right, great. Any questions about that one? It is bounded. Okay, the next one, n e to the minus n. So these ones are, the last two here are slightly more complicated. N e to the minus n. I hope everybody remembers e to the minus n is the same as like 1 over e to the n. So this, you could also write it this way if you like. All right, and if you were to write out a few terms, it'd be 1 over e, whatever that is, and then 2 over e squared, and then 3 over e to the 3, etc. All right, these are a little weird, like I don't especially know what those numbers are without using my calculator, but one thing I can tell you is they're all positive, so that means this is bounded below by 0. This is like an obvious thing that you should be looking for if the terms are always positive. Or if they're always negative, you can immediately say that so this one is bounded below by 0. All right, because they are all positive. Yeah. What about bounded above? Did anybody say anything about this? Is it bounded above or not? What I'm asking is there some number that these are all less than? I suppose you could try to plug those guys into your calculator. I don't know. Any thoughts? You could also think about this as a fraction and think something about the numerators and the denominators. Anybody? Yeah? It's bounded above by 1? Is that what you meant? Yeah. Why 1? I think I agree.
I think I just think because it's a fraction.
Yeah, because it's a fraction, and if it's a fraction where the denominator is always bigger than the numerator, then that means that fraction is less than 1. Are you sure the denominator is always less than the numerator? Bigger, sorry. Is e to the 3 actually bigger than 3? It is, although I don't know how obvious that fact is. E is a number like a little bit more than 2. And so this denominator is something, I suppose, like more than 8, and so that's definitely bigger than 3. So you could think of it in that way. These are fractions in which the numerator is always bigger than the denominator. I think another way to think about this is kind of, I'm asking, is this thing bounded above, or do these values go up forever? One way to answer that question is by thinking about the limit of this sequence. If I'm asking you, do these values go up forever? Actually, they do not. You can see that the limit of this is 0. That's because if you make n go to infinity here, you get something like infinity over infinity, and you would do the L'Hopital's rule, and then you would get 1 over e to the n, which goes to 0. That means the limit of this sequence goes to 0, so the sequence does not go up forever. All right? I don't know exactly. It might go up a little bit and then come back down to 0, but it certainly does not go up forever. Anyway, either way, this one is a little tricky, and I'm not sure what exactly I would expect you to write for this, but this is bounded above. It is bounded above. All right. I would say, to explain that, you could say, one thing that you could say is something like n over e to the n has bigger denominator. So n over e to the n is always less than 1. Or you could say, here's just another way of explaining it, n over e to the n converges actually to 0. So it can't go up forever. All right, that means it must have an upper bound at some point. If it converges to 0, then it does not go up forever. All right. All right, great. And how about the last one? Negative 2n over n squared plus 1. This was meant to be similar looking to that very first one that I discussed, n over n squared plus 1, only it has a negative 2 on the top instead of, what it used to have, just a n. I'm going to bring this down a little. This one also, you might think about just starting off by writing some terms. I would start with negative 2 times 1 over 1 squared plus 1, and then negative 2 times 2 over 2 squared plus 1. This is negative 2 over 2. This is negative 4 over 5, etc. All right. Any thoughts about this one? Is it bounded above? Is it bounded below? Let's talk about above first. That is, I am looking for a number which is bigger than all of these fractions. Any ideas? I saw some folks said so. Someone's giving me the signal of 0. 0 is bigger than all of these fractions, right? They're all negative numbers. You can tell just by looking at this formula here, this must always be negative because the n's are always positive. So here, an is always negative. So an is less than 0, so it's bounded above. Right, that's what it means. When things are always negative, that means they are bounded above by 0. And what about bounded below? Again, this is an example where you have fractions and the numerators are always bigger than, the denominators are always bigger than the numerators. 2n plus 1, here they're equal, but otherwise the denominator is always bigger than the numerator. And so these, I suppose, like that one right there is kind of like the most negative one. What it looks like is these fractions, these are negative fractions, and they are approaching 0. That's because the denominators are going to be bigger than the numerators. And in fact, when you look at this, like looking at this fraction here, I could tell that the power on the bottom is bigger than the power on the top, and so it's will approach 0. That means if you were to imagine what the kind of chart of these looks like, they all look like this. They are negative and approaching 0 like that. That means they are bounded below by, something down here. I'll say like -2 is the lower bound for all of those. All right. Ordinarily, I would pick -1, although the first one actually equals -1, and I need a number which is lesser than all of them. So I'm not going to take -1. I'll go down to -2. So here, these are bounded below by -2. All right, that one's a little tricky, I guess. It's because they are all negative, first of all, and they're fractions where the bottom is bigger than the top. All right, here's my -2. Okay, great. This is boundedness. All right. I would like to discuss what is the relationship between boundedness and converging, because you can tell there seems to be some kind of relationship. Like this one here, so we said this one is bounded above, this one is also bounded below, so AN is bounded, right? This one, actually it does converge. It converges to 0, and it is bounded above and below. Is there some kind of a relationship between converging versus boundedness? So I want to talk about boundedness versus convergence. Is there some relationship between boundedness and converging? All right. It turns out there is a relationship. Like this is an example where it's bounded, and also you can see this one converges and it is bounded. This one also converges, and we said it is bounded, right? It was bounded above, I said here, and also bounded below by 0, right? So this one, it converges and it is bounded. What about this one here? This one does not converge because it goes up forever, and it is not bounded. It was bounded below but not bounded above. So there's a very close relationship between boundedness and convergence. I think it's not so hard to convince yourself. Any converging sequence, convergent is the word we usually use, any convergent sequence is automatically bounded. All right, that's because if you just think about it on a picture here, all right, a convergent sequence, it means when I draw the dots, like I don't know what they do at first, but eventually them dots have to actually converge to a particular value like this, right? This is what the picture of a convergent sequence looks like. It might do some weird stuff at the beginning, I don't know, but eventually, beyond a certain point, all of the values are basically are getting super close to a particular number. All right, this is a picture of a convergent sequence. And is this one bounded? That means, can you sort of like draw a line above everything and also another line below everything? The answer is yes, you can. And actually, that will always be true, because as long as it converges to a particular value, you can always just draw some sort of window that encompasses the tops and the bottoms of the sequence, right? That's always possible. If you think about, like, what would the alternative be? The alternative would be if somehow the dots kept on going up forever, but that's impossible if you know that it converges. All right, so this here, you can always sort of insert that upper and lower line. So if AN converges, there will always be some upper and lower bounds. All right. So converging means that it's bounded. I could say it that way. Convergent, this is how we sometimes would write this. Convergent implies bounded, right? If it's convergent, then it is automatically bounded. The natural thing we always ask when we have one of these sort of arrow implications like that, can it go the other way around too? What about bounded implies convergence? Is that also true? If you know that the sequence is bounded, does that automatically mean that it converges to some value? Actually, it is not true the other way around. And we had one of our examples of the ones that I just asked you to do. The other way, t'other way, isn't always true. That is to say, it is possible to be bounded but not convergent. Anyone know what I'm thinking of? Actually, one of the examples I asked about a moment ago. Yeah? Yeah, -1 to the n. So this is an important example of this phenomenon. an equals -1 to the n. So this one, if you were to draw, the dots, it looks, it starts negative. Looks like this, right? And I hope everybody will agree. This one is bounded but does not converge. It doesn't converge because those values are not getting close to any one particular value as you go off to the right forever. All right? This one is bounded, by +2 and -2. You can put sort of the window around that sequence, but not convergent. All right? So convergent implies bounded. The other way around, it is not so. Bounded does not imply convergence because it is possible for a bounded, it's possible to have a bounded sequence which does not converge. All right? Such as that one right there. It is bounded, but it's not convergent. All right, one last thing to say about this, and then we're going to talk about serieses. There is an important theorem about these things. I'm going to say, and this is an important case where bounded actually does imply convergence. So it's not always true, but there is one important situation in which actually, if you know that it's bounded, then it will converge, and that is for monotone sequences. Check it out. So I'm going to write this down as a theorem, and this is sort of a big and important theorem. It's called the monotone. I wrote too many. Monotone convergence theorem. The monotone convergence theorem. And it says, if an is bounded and monotone, then it converges. All right. Usually bounded is not enough for converging, but bounded and monotone, actually, this does converge. All right. So when someone asks you, like, hey, if a sequence is bounded, does that mean that it converges? The unkind answer is no, you idiot. It just doesn't mean that. Bounded does not mean that it converges. But if you want to be nice about it, you could say, well, no, honey, but if it's bounded and monotone, then it does converge. All right, that's what the monotone convergence theorem says. And I don't want to talk about a proof of this necessarily, but it's not so hard to convince your dear friend, your dear misguided friend, that this will be true. If it's bounded and monotone, check it out. What does that mean? If it's bounded and monotone, so that means my sequence, if I already know it's bounded and monotone, so this, I'm going to try and draw a picture of what it means to be bounded and monotone. It looks like it's a sequence where, first of all, it's bounded. That means there's some like upper bound and lower bound. That this sequence always, like all the dots I'm going to draw, they have to be in between those two horizontal lines. And it's going to be monotone, and I hope everybody remembers, monotone means it's either increasing or decreasing. So what I'm going to draw some dots. They have to either always go up or always go down. So those would look different if I drew one or the other. I'm going to draw it as if it were increasing, but of course you could also draw them being decreasing. So I'm drawing the dots in such a way that it's bounded and monotone. Let's say I'll start down here, I don't know. But I'm going to draw them increasing every time, just because I have to draw monotone. That means either increasing or decreasing. I'm going to draw them as increasing. Well, okay, so I'm going to draw some dots. They got to go up every time, right? They got to go up every time, but they can never go above that line up there, right? The big M. What does that mean? It means they're going to have to converge. Like, they can't go up forever. They can never go past that big M, which means it's going to have to converge, right? There's no way. And you might say, well, what if instead of going up to that M, what if it just like bounces back and forth? You know, maybe like this, right? There, that doesn't converge, and it stays in between the things. But okay, but that's not monotone, right? Remember, I said it has to be monotone, which means either it's always going up or always going down. So bounded and monotone, the picture basically looks like that. Either the dots are always going up, in which case they're going to converge at M, at the upper M, or perhaps they converge somewhere lower down. Or the dots are always going to go down, which means they're going to converge at the small m, or perhaps converge somewhere else above the small m. All right? Anyway, it converges, right? This is the monotone convergence theorem. It says, so bounded by itself does not mean that it converges, but bounded and monotone always converges. That's the moral of the story. All right. Excellent. Any thoughts about that one? This is all we needed to say about boundedness and such. All right, great. We got some time left today. We can talk about series. Monotone convergence theorem is super important. You will see it again if you take our real analysis course, which is all about such things. All right, let's talk about series. We've talked about sequences so far. Let's talk about series. I don't really like this. The word series is a singular, and the plural of the word series is also series, which never struck me as correct. I say series sometimes. I know that sounds stupid. Anyway, what's a series? So this is not a synonym for the word sequence. A sequence is a list of numbers one after another. A series is what you get when you add all of those numbers up. So a series is the sum of all the terms, and this means like infinitely many, the sum of all the terms from a sequence. All right, so if we start with a sequence an, so this is what a sequence is, an, we can consider the series of an. The series is this, the sum n equals 1 to infinity an. All right, and series are more complicated than sequences, I suppose, just because a series always involves an infinite sum, which is always a little weird, right? But that's what we're here for, talking about weird stuff like that. These series are actually super useful in all kinds of situations. You may think it's weird to add together infinitely many things, and I would say, yes, it's weird, but it's useful, and it does make sense if you are careful about doing it properly. All right. So sequences are just the numbers one after another. The series is what you get when you add them all up. We actually saw an example of a series when we were talking about improper integrals. So from sort of a long ago, I tried to explain how this, if I add up 1 over 2 to the n equals 1 to infinity, this actually adds up to 2. I said something about if you're adding up the, 1, it's not 2. If you start n equals 0, you get 2. If you start n equals 1, you get 1. And this, unfortunately, is a technicality that we're going to have to care a little bit about. But why is this true? So this series, you should think of, if I were to write out a few terms of the series, it's 1/2 plus 1/4 plus 1/8 plus, etc., right? Rather than a sequence, you would write little commas in between. A series, you just write pluses. You are adding these all up. And I don't know if you remember this, but I tried to explain sort of on a geometric level. If you imagine, say, a big unit square, and if I stack little blocks, the lower half of it, of course, has area 1/2. If I now consider the upper half and cut that in half again, this has area 1/4. I'm going to divide it again. That's a 1/8. This here, that's about as small as I can write, is a 1/16 area. But it is true, if you add all of these fractions up, they don't actually extend forever vertically here. Actually, each next fraction here will just kind of slide in as half of the remaining space, which means if you sort of in the limit, and we'll talk specifically about how you really do this calculation, but in the limit, if we add all of them up, it fills exactly this square, which has area 1. That's why this sum of this series actually adds up to 1, all right? It's weird. Anyway, the big questions are sort of how do we calculate the value of the series, what the series adds up to. Like in this example, I drew some cute little blocks, but of course we don't want to do it that way in every example. So we would like, I don't know, some kind of formulas or some kind of general method by which we can always just figure out what it adds up to. That's the major question, although for today at least, we're going to talk about even before you even get to that part, a more preliminary question would be what does it even mean? What does it even mean to add together infinitely many things when you talk to your friends at lunch about what you talked about in your math class this morning? Try that for a little April Fool's prank. We talked about adding together infinitely many things. Their reaction is likely to be that's stupid, or what are you even talking about? Or what is that even, what does it mean to add together infinitely many things? So that's the question that I would like to focus on, at least at first. What does it even mean to add together infinitely many things? And how can you say what the answer is? I mean, how can you even make sense of it at all to ask what that is? So let's talk about what it means first of all. All right, if we have a sequence AN, right? We can consider adding together the terms, adding it up. Now, if you immediately say, I'm just going to add up infinitely many things, then my question, of course, will be, what are you talking about? What do you mean add up infinitely many things? That is something that on its surface doesn't make sense, but I can do something that makes a lot of sense. It's very simple. I can consider adding it up sort of one at a time. I could just take the first one by itself, and then I could take A1 plus A2, that's the first two of them, and then I could take the first three of them, A1 plus A2 plus A3, A1 plus A2, you get it, A3 plus A4, etc., right? And even your friends at lunch will have to agree these do make sense, right? There's nothing weird about this. I'm just considering, just add a few of them at the beginning, all right? And you could continue this as often as you like. Actually, we have names for these things. I'm going to call this S1. This I call S2, S3, S4, etc. All right? So in general, what I'm talking about is I'm just inventing a new sequence. We started with the sequence of A's. I'm creating a new sequence which comes from adding together some of the A's. And the definition is Sn equals A1 plus A2, etc., all the way to An. All right? And this is a new sequence, and this is called, this has a name, this is the sequence of partial sums. partial sums, meaning it's not that I'm adding together all of the terms, because I'm not. Each of the S's represents adding together only a part of the sequence, right? That's why it's called the partial sums. They are just summing the first part up to a certain point, all right? This is called the sequence of partial sums. Of course, you could also write it this way: Sn equals the sum, n equals, well, I'd have to change the n's. I don't want to use n too much here. I would say something like I equals 1 to n of ai, right? You add them up, starting at 1, going all the way up to n. That's what the sequence of partial sums is. And now that you see this, I think it becomes clear, how do you define what it means when you add up infinitely many things? We define the series n equals 1 to infinity, ai, as the same thing as lim n goes to infinity of Sn. All right? And this is what it means when your friends ask you, what does it even mean to add together infinitely many things? Your answer to your friends should be something like, well, if you want to know what it means to add together infinitely many things, you think about what do you get when you add together not all of them, but just some of them? You add, say, the first 5 of them, or the first 6 of them, or the first 7 of them. You do all of those, and you take the limit as n goes to infinity, and that's what it means to add together all infinitely many of them. You imagine adding all of them up to a certain point, and then you take that point to infinity. All right? So this is the true definition of what it means to add together the terms of a sequence. So every time you see the series, so any, sorry, I wrote AI there. It should have been an N. There's no I in this formula here. It's N. Sorry about that. Although this I is supposed to be I, but this should be an N. So any series, sum of an, like that, is actually just the limit of its sequence of partial sums. All right? And the limit of a sequence, we already know what that means. It means what did the terms approach as you look further down the list. All right? It is the limit of a sequence. What that means is, since it's a limit of something, it's possible that it could exist or not, right? Because we all know that limits can exist and sometimes they do not exist. So because every series is a limit of something or other, it's a limit of a sequence, that means that any series, so a series may converge or diverge, depending on whether that limit converges or diverges. May converge or diverge. Because a series is a limit of something, and limits can either converge or diverge. So if I ask you, eventually we're going to get to lots of problems where I show you a series and I ask you, what does the series actually add up to? Your answer is either like it adds up to something, like it adds up to 1, or maybe you might say it diverges. All right? Great. Let's talk about some simple examples. And then, eventually we'll get to less simple examples. But how about, this is everybody's simplest example. How about an equals 1? This is just a sequence which looks like 1, 1, 1, 1, 1 forever. All right? If I were to write out the terms, this is a constant sequence with value 1 every time. And I would like to know, your job, find the series n equals 1 to infinity of an. All right? Your answer is either going to be a number or you say it diverges, because a series like this is allowed to diverge. All right? if you are thinking along with me, I think this one is fairly obvious that it does not add up to a particular number. Think about what this means. AN, of course, is just 1 every time. So this means this, just plugging it in, is 1, right? It is the sum of 1 from n equals 1 to infinity. That means I'm doing 1 plus 1 plus 1 plus 1 infinitely many times. This does not add up to a, 8 or something like that. It basically adds up to infinity if you want to say it that way. But your expectation should be that this is going to diverge, right? If you just add 1 over and over again up to infinity, it does not converge to any particular answer. Okay, but we should try to demonstrate this carefully. How we demonstrate this is we consider the partial sums. So the partial sums. All right, S1 is just the first term by itself, which would be 1. S2 is the first 2 terms, which would be 1 plus 1. S3 is the first 3 terms, which would be this. All right, etc. Hopefully by writing down some of these partial sums, we can come up with some kind of a pattern here. Of course, 1, I'm going to simplify here. 1 is just 1, right? 1 plus 1 is 2. 1 plus 1 plus 1 is 3. So in general, can you say Sn equals, I want a formula over here in terms of n. What do you think? I said S2 is 2, S3 is 3. Do you see the pattern? I think you do see the pattern. It's very...
Is it Sn equals n?
Sn equals n, yeah, it's a simple pattern. S4, if I went to the next one, would be 4. S5 would be 5. In general, Sn equals n, all right? This is kind of silly. I mean, if you're paying attention, I hope you agree this is very simple, but this is what's necessary in order to find the value of the series. So the sum, n equals 1 to infinity of an, this is the definition. It is equal to the lim n goes to infinity of Sn. So this is lim n goes to infinity of n, and that is infinity, right? Or you could say it does not exist, or whatever, it diverges. All right. This is how you find the actual value of one of these series. First, you determine what is the sequence of partial sums, and then you take the limit of that sequence, and you can tell if it diverges or not. All right, so in this example, the sum n equals 1 to infinity of 1 diverges. As it should, right? It would be profoundly weird if this actually added up to a specific number. It doesn't. When you add together 1 over and over again, it diverges. All right, great. This is not surprising at all. The next example, maybe slightly surprising. I don't know. What about this? The sum negative 1 to the n going from 1 to infinity. All right. This is the same as before, only with a minus 1 to the n instead of a 1. Now this one is a little strange in my opinion. Of course, if I were to write out the terms here, they are alternating negative 1, positive 1, negative 1, positive 1. And what I'm suggesting is you add them all up. So if I were to write this out in terms, it would be minus 1, well, can I just say minus 1 and then plus a positive 1 and then plus a negative 1? That's like this, and then plus a positive 1 is this, right? I don't know if this is something you ever wondered about as a kid on the playground. Do kids talk about this on the playground these days? What do you get if you add together negative 1 plus 1 plus negative 1 plus 1? Yeah? Does it add up to 0? This is the natural thing to consider. This thing, it seems to me, it would make sense to say this all adds up to 0. Anybody disagree with that sentiment? Actually, there are some reasons why you might say, actually, I don't think that should add up to 0. The first objection, of course, is like, I don't even know what you're talking about by saying you're adding together infinitely many things. But actually, we do know what we're talking about now. Here's one reason why you shouldn't think that this, could I just say, maybe not 0, Although I think it does make sense on some kind of intuitive level to say, like, these should all just one by one cancel each other out and you should get 0. Although, check it out. How about this? This is what I would say to you on the playground if you told me, I think that just all cancels out and you get 0. Check it out. What if I only look at this part? What would you say this part adds up to? I would say, for the same reason, that part also adds up to 0. But now, as they say on the playground, now you're tripping. If you tell me the whole thing adds up to 0, but also this part of it adds up to 0, well, this part of it, if this part adds up to 0, and then I have an extra -1, that means the whole thing adds up to -1, right? But you just told me the whole thing adds up to 0. So there's something weird about this. This is, I would say, the reason why you should not necessarily think that the whole thing adds up to 0, because this seems to be 0 also, which would suggest, if the red part really is 0, that would suggest the whole thing is -1, which doesn't make a whole lot of sense to me, all right? Anyway, the answer is it diverges. This is the true answer to this. It actually does not add up to 0. It also does not add up to -1 or to +1. It turns out this whole sequence, or this whole series, diverges. Can we try and demonstrate that? Actually, it's not hard to demonstrate this at all. Turns out it diverges. This is just because when you're dealing with adding together infinitely many things, weird things can happen. And it might seem more ordinary to you to make it add up to 0, but actually even that would be very weird. And the true fact is that it diverges. Check it out. I'm going to try and do just like we did up here, right? We're going to write down the partial sums, see if we can see a pattern here, and then ask about what the limit is. So I'm going to write down the partial sums first of all. S1, the very first term is a -1. S2, the next term would be -1 plus 1, right? S3 is -1 plus 1 minus 1. S4 is -1 plus 1 minus 1 plus 1. You always just write out the first sort of block of terms. And what are these values? We can add them up. So the first one is -1. The next one is 0. The next one is -1 again. The next one is 0 again, etc. So the pattern this time is you either get -1 or 0, depending on if the thing is even or odd, right? So generally speaking, and this is not something you can easily write as a formula, but I will say Sn is 0 when n is even, and it's -1 when n is odd, right? There isn't an especially nice formula you can write for that, but this is what it is. It's 0 when n is even, and it's -1 when n is odd. All right, if I were to, you can very easily draw sort of a little plot of these terms, right? They look like this: -1 and then 0, -1 and then 0, like that. Sort of off the bottom. All right. So what is the value of the series? So the sum of an, n equals 1 to infinity. That, of course, is the lim, n goes to infinity, of Sn. And what is that limit? It's the limit of this, and there is no limit, right? Because these values do not approach any particular value as you go off to the right forever. So this diverges. It doesn't go to infinity or anything like that, but it doesn't converge, and so it diverges. All right. So to answer the kids on the playground, I would say -1 plus 1, -1 plus 1, -1 plus 1, etc. This has no value. It doesn't add up to 0. If you think it adds to 0, this actually causes more confusion, but it certainly doesn't add to anything else, though. So this the series diverges, which means there is no answer when you add up those numbers in that way. All right. Any thoughts about that? All right, I got one more thing to say, and this will be maybe a little introduction to next time. I would like to, like I said, talk about some general techniques or formulas that you can use here. This is still a little cumbersome to like write down these terms here, see if you can find a pattern. In this case, we had to draw a little picture to convince ourselves. All of that is a little cumbersome to do in general. Some general principles or general formulas, I would say we can always work this out. We can work it out nicely for geometric sequences. Geometric sequences. Sorry, my handwriting is not so good today. We can work it out nicely for geometric sequences. Geometric sequence, I hope you recall from last time, is something that looks like powers of a number, like 2 to the n. That looks like, 2 squared, 2 cubed, 2 to the 4, right? These are sequences that look like this. A to the n equals some number to the power n. And I think we called that number r. Last time we talked about this, r to the power n, and we had some rules about when this converges and when it doesn't converge. So this, if you recall, this diverges, well, it converges. Did we call this number a before? Sorry, I'm blanking on what I called it last time. We talked about this at length a few times. Yeah, I called it r. All right, so this equals r to the n. Remember from last time, it converges when the absolute value of r is less than 1, and it diverges when the absolute value of r is greater than 1, right? This is something that we talked about last time. And in fact, it converges to 0 when the absolute value of r is less than 1, and it diverges when it's greater than 1, all right? So, since we already know fairly well what the sequence does, it's not so hard to sort of translate this knowledge into asking about what about the series, all right? The trick here is that it's a little difficult. So my next question is, what about the series r to the n, right? Adding them up. We already know, depending on what r is, that sequence by itself either converges or it doesn't. But what about when we try to add them up? So we can do the partial sums here, although it turns out this is sort of for technical reasons. So this is n equals 1 to infinity. Actually, it's easier to consider the sum n equals 1 to infinity of r to the n minus 1. Well, you'll see why, but this one begins, the exponent is always going to start off as a 0. So it's basically the same series, only it starts with the exponent as a 0 and then 1 and then 2, rather than, if you write it this way, the exponent starts as a 1. That's the only difference. So this, if you write out the terms here, it begins with r to the 0, which is 1, and then plus r squared, r cubed, etc. All right. This one turns out to be a little easier to handle just because that extra 1 on the front makes everything work out slightly nicer. All right. But anyway, let's try to do our same old approach, which is to say I'm going to write down the sequence of partial sums. So the partial sums, just because that's the only way we have to get a handle on these infinite sums, is by the sequence of partial sums. Okay, the first one is 1. The next one is 1 plus r. The next one is 1 plus r squared, etc. Generally speaking, the Sn is 1 plus r squared, all the way up to r to the power n minus 1. It's because of this n minus 1 here. All right. The S2 only goes up to r to the power 1. The S3 goes up to r to the power 2. So it's always the n minus 1 power over there. All right. Unfortunately, I don't really like the way that this looks, but this can be simplified, and here's a trick for simplifying. This is a weird trick, which You don't have to do this. I mean, we're just going to do it this once and then just kind of remember what the result is. So the trick to simplify is multiply by r on both sides. It says r times Sn is, and on the right side I'm going to multiply everything by r. This has the effect of just like increasing all of the exponents by 1 because I'm multiplying through by r. So what used to be 1 is now r, and then r becomes r squared, r squared becomes r cubed, etc. And then the last one, which used to be r to the n minus 1, we increase that power by 1 and it's just r to the n, like so. All right? This is Rsn. And now, check it out. I'm going to write this down right next to Sn. I know we got to go in a moment. I just want to finish this so that we can start off with a very nice looking formula. Check it out. We are going to subtract one from the other. I want to subtract Sn minus Rsn. Sorry. Subtract here. Subtract these two equations from one another. It'll say Sn minus Rsn on the left. And on the right, actually on the right, almost everything will cancel. These, I have r and r will cancel, r squared, r squared. This r cubed will cancel with, the r cubed that was up there. Everything, I believe, cancels except for the 1 at the beginning. It has nobody in the lower one to cancel with. And this one actually does cancel something here, but the r to the n at the end here doesn't have anything to cancel with. Everything else in the middle cancels out. So what I get on the right-hand side is 1, which did not cancel, and then r to the n, which did not cancel, but it's minus r to the n because I was subtracting the top one minus the bottom one. All right? But check it out. Here, we can solve for Sn. I factor on the left, Sn 1 minus r, and then finally, like so. This is a formula for the partial sums, and here we can do, I will leave you with this. This is a formula, and you can just because this is an ordinary looking fraction, you can do the limit as n goes to infinity. And that's the purpose of doing the series. Of course, you write the partial sums and then take the limit. So this one actually is appropriate for taking limits. All right, we'll start with this formula. This is a weird trick. Like I said, you don't have to remember how to do this trick. You got to remember this, though, what you get at the end. All right, see you all tomorrow. Let me know if you want to talk about the homework.